you 50 minutes to become an expert. So look at this one. We went through this last time. I think we stopped at this example. We were talking about, I think, where's the dash line? Here's the dash line. Okay. And there's an unwell because this box, this bigger box with this dash line is an unwell. You can see it's an unwell. So unwell is inside the P substrate, the P-type substrate. So you want to draw unwell first. And because you have a P-select, remember I talked about this last time. Is that P-act or P-select opens up Fox? Wait. Look at our notes. Yeah, P-act opens up Fox. So why P-select is larger than P-act?
Does the P-select like fills in the gap that P-act needs?
Mm-hmm. So here's Fox, right? Because P-act opens up Fox. Because we are trying to avoid misalignment issues, so we make a P-select a little bit bigger, because P-select will be a window that allows the P plus material, which is part of the transistor, it's called diffusion, to be doped into the certain area over here. So eventually there will be a P plus being doped into the wafer. And you need a bigger window for P-select because there will be a misalignments. And you want to make this bigger so we can make sure that this area, all of this area can be doped by P plus. If you just make it the correct size, if there's a misalignment, then you are missing a little corner on the edge, right? Okay. So for this one, could you see P-select? So the P-select is the solid line of the box over here. It's a little bit bigger, and we are drawing that P plus, and you don't want to look at this line because you can see this line comes down here. It actually hit the Fox. It just some minor details, and you'll lose points from the quiz. So make sure that you are drawing an accurate outline of everything. If it's not on the quiz, it's going to be on the exam in the future. And one question here, why this P plus has a little gap in the middle? Ground?
We don't actually know what's there because the poly is covering it. Or is it the field oxide?
Mm-hmm. So the thing is, if you have a P select, and in the process, and this is going to be a window, and all this area will be covered by P plus. But the thing is, there's no P plus here. How could you control that?
It got covered.
It got covered by what?
Probably the
Poly.
Yeah.
Yeah. So the question is, should you put the poly there first and do the P select one by one, or you should place the poly there first and then do the P select or the doping?
Place the poly there.
Put the poly there first and then dope it, the whole area, the whole window here with P plus. What's the benefit of doing that? Imagine you want to do this one accurately, have a little P plus opening here, and do this one, and you want to just have a defined opening over here, so you have a certain gap, and move it next to the right hand side, and then dope this area, so you have this gap, and then you find this area, and it's actually etching, so you have a homogeneous layer of poly, and then you etch it away from the rest, away from the wafer, and you just leave this wire on the top. So we just leave this wire on the top, so we got a gate, and it's directly on the top of the opening here, of the gap here. Thinking about the terms I use. You have a little opening, since we designed to have a little opening here, and then I'm trying to do, because everything for the chip design or the fabrication is bottom-up process. It's starting from the bottom. Okay, so you do the unwell first, definitely, and then you open up and do the doping, and sometimes you have to do this first because it matters. Okay, so same concept. We don't want to do these two individually and then place the gate on direct on the top of this gap, because there's no way that I can accurately control that. already told you, even you have this opening, you still want to make this P selector bigger to avoid the misalignment issues. So the misalignment issues also happens to this one. If you've got a gap here already and you want to place a poly wire directly on the top of the gap, it's hard. So in that case, you put the poly here first, and then you start doping the area, and because this is blocking this gap, so it's going to directly leave a gap or opening underneath the poly. Exactly. Does that make sense? So you have something on the top. It's like an umbrella on top. So when it rains on top of the umbrella, but not whiting the whatever underneath it. So in that case, we can design a very simple P-type transistor. This is a P-type transistor, and this is a transistor. It's done. It has a drain, source, a gate, channel. So if you inject current in here, and if it's, for example, it's getting turned on, the gate is getting turned on, and current is going to flow through the channel in that way, or the other way around, doesn't matter, depending on the polarity of the voltage source. But it's gonna flow in that direction. So that direction is when you see this one, it's like a pie, right? Like the wafer, the whole wafer is like an apple pie. You cut it, and then you look from the side as a cross-sectional view, and it's gonna run this way. So in that case, the electrons or the current travels in this dimension, and this dimension is called the length. That's the length of the channel. So where's the width?
Be like the
It's into the paper. That's the width. Okay? Into the paper is the width. So when we are talking about C5, we're talking about 180 nanometer technology from TSMC, or talking about 5, or now 2 nanometer technology from TSMC will become available very soon. So 2 nanometer technology means the length. Keep in mind, doesn't matter, it's 500, 180, 28, 7, 5, 2. They are all talking about the length of the channel. So that's the length of the channel, not the width. We'll get into the details of the transistor operation later. But now you should know that this is the length, and the current travels along the length. Okay. If I draw a line here, are you able to draw a cross-sectional view of it? Let's do it.
Yeah.
Remember, it's a bottom-up process. One more quick note here. Did you see this uppercase L? What is that?
Length.
That's a length. Okay? So it looks like the width of the wire, of the poly wire, but the width of the poly wire defines what? The length of the channel. Okay? Because it blocks the P plus diffusion getting to the wafer. Now let's draw it. Bottom up. So here's the N select, here's the P select, definitely, or N act and P act, and you know that for this area there will be an opening. So, but the rest will be a Fox. There will be an opening. It will be like this. Fox, Fox, Fox. And N-well covers the whole thing pretty much. So I just draw N-well. I mean, you can see in the example over here, they drew the Fox line on the top, which is, it's just a line. It's okay. So just draw the line over here. It's not a big deal. This is making any differences. Let's see. done this way. Is there a poly? Yes. Is there a P for this guy? Is there a P plus? The P plus blocked by the poly? Yes. So we got a poly here. So it's on top of it. Here's the poly. And here's a P plus. Am I making it right? Yeah, that's right. Here, you have N plus, the whole area here is N plus, and there's no poly, so it's not getting blocked. So the whole area here is just N plus. And if you look at the line here, it doesn't cover anything else. It's just N well, an N plus. It's done. That's it. You don't even have metal. There's no metal, no via. Right? So the difference between this one and the one here is that this one has, this crosses the vias and metal one. So you have to draw the vias and metal one here. But for this one, it skips it. It's on the side.
In between, so like where the P plus and Fox layer, and then up to in one where the vias are drawn on the first diagram, is everything kind of besides the via and the poly, is that all just an insulator?
You mean this area? Here? Or
Yes.
here? Yeah,
Yes.
it's an insulator, yeah. Silicon dioxide. Yeah.
And then there would still be the like insulator layers where the M1 and 2 would go, right?
Yeah, yeah.
Okay.
Yeah, yeah. Good question. We should draw them, okay? So here's metal 1, here's metal 2, here's metal 3. But nothing in there, in them. Let's look at this one. I'll let you guys start drawing it. And I'll let you compare with mine later. Okay? Give you several minutes to practice.
When we're drawing them, do you want them like drawn to scale, like directly lined up with the edges?
We should, yeah. Keep in mind that this is a little bit confusing. Sometimes they put the Fox layer on the top. Sometimes it's just directly put it in line with the P plus and N pluses. I think either one is fine. I don't really care because in the real device, if you look at the cross-sectional view from the SEM, the scanning electron microscope figures of the chip, it's not exactly a straight line. It's a little curve here. Okay, so either way works. Alright, let's, if we follow the same convention, draw a substrate first, it's a P sub. And it seems like this is only P act or active component, so this is the only part that has an opening. So all the rest should be covered by Fox. However, this area will be P plus. And going up one layer will be the poly layer. This poly layer has this. So keep in mind that the poly layers are not directly making a contact to the bottom. The reason for that is a lot of times it's trying to create a little gap between this poly layer itself and the layer underneath it, and it's called gate oxide, and that is why there's no direct contact between the gate and the diffusion, because they are trying to generate a little dielectric material in the middle. Even though the gate oxide layer is super thin, but there is a gate oxide layer on it. So we'll draw poly, that's why it's like floating in the middle. It's not directly touching the bottom. So
Yeah, so why is the poly above the Fox?
yeah, because we want to keep, for example, this poly doesn't make sense, it's just a drawing in the textbook. But now, just in case, if we are having a gate here, for this example, right? See the poly is in the middle? It's forming a transistor. And forming a transistor, we do need a little dielectric material here to not directly make the current flowing into the channel. So because that's how the NMOS transistors are being designed, and they are how they operates. So the way to do that is that you connect. You see, this is the gate. This is the drain, the source of the transistor. And from the symbol, you can tell there's a gap. It's exactly the gap I'm talking about. They draw the symbol in the same way. However, for BJT transistors, if you're in analog, is there a gap? No. So the base is directly contacting that NPN, the P junction here. It's making a direct contact. But this one is not making a direct contact, that's why I'm drawing a gap in the middle. So the way that works is, it's whenever you apply a positive voltage at the gate, it's creating an electric field instead of directly injecting current into the channel. We don't want that to happen. I'm going to explain that to you maybe, I think it's going to be Friday's lecture. So that's how that works. So it's creating an electric field and to attract electrons in the channel. So the electrons are actually making up a channel. Okay, so it's not conducting, but it's attracting electrons to form a channel, a layer of electrons. That's how that works. And then you give a pressure at the drain, give a potential drop, and the electron starts flowing that way, and the current starts flowing that way. Okay, that's how that works, like a switch. But you have to form that channel first by the electric field. Okay, that's how that works. So the gate is not making a direct contact with the channel because you want to create the electric field instead of injecting direct current to it. So we don't want to injecting current or taking current out or away from the channel. Sense? Okay. For this one, that's how we know that poly is floating in the middle, and we have metal 1. No matter what, have to draw metal 1. So metal 1 is a long wire here, and metal 1 is basically making a contact to the bottom. You can draw it that way. This is poly. It's metal 1. And why metal 1 needs to make a contact with the bottom? Why is that? So via can conduct currents with it, right? So you have one via here, another via here. But poly doesn't need to have any direct contact with anything underneath it. But you do need a vias above it. And since metal 1 is touching the bottom, so it's making things possible. Does that make sense?
Yeah.
It's doing everything layer by layer. The height of the via actually defines the layer's thickness of the poly layer, right? You're thinking about, can we just have this one intruding into the metal 2 layer if metal 1 is not touching the bottom? I mean, wherever the via stops, it defines the width or the height of the metal 1 layer, you know? So it's just because this line has to be a straight line. It's doing a spin coating and making everything homogeneously distributed on the wafer. It's straight. It's flat. Any question on this example? Easy, right? Now let's look at the next one. Draw the substrate first. See what's the dashed line here? What is this?
That's the P-plus.
It should be unwell. It's not labeled, but should be unwell. Let's assume it's unwell. Right? So you got a P select. So P select within the P select is a P act. This is a P act. So no Fox, but here you got Fox. And here is unwell. Now this one. Sorry. Here is unwell. Got poly? Nope. What is this piece?
Which piece?
I mean, what is this thing in the middle? Do you have a poly? There's no poly, right?
No, it's Vias.
V is on the top of what?
That one. Or just on top of P-select.
I'm not sure if I drew metal here,
I thought that's just the.
but there should be metal because usually this device has a metal one with it. What was it?
The P plus.
Just a P plus, yes. So here should be P plus, right? And then what? So I have no poly, right? No poly.
So then you look like the little bars that are next to it.
Do you need the poly in the middle as a bridge to make the connection between P plus to metal 1?
No. No, you could just.
Yeah, just have a bigger via, longer via. So what's happening here? Since you have a via, usually if you have a via, there will be metal 1. It just didn't tell you. But I can see actually it has it. Did you see this box over here? Even though it's not super visible, but did you see that? Within that green area, it's not showing green here, but within that active area here, right? This is the active area. Right here's a box. You see that? Okay, so that box is actually a metal 1. So this is metal 1. Usually the vias comes with the metal 1, or metal 1 comes with the via. It's actually a library component. Whenever you grab a piece like this, you can define the length or width of it. And this component from the library is not really asking you to modify it. So it's making things easy for you. So it's directly have a metal 1 on it, and also a P plus underneath it, and vias in between them. So if you draw it, it becomes a little, no, actually not little ones, but metal 1. This is metal 1. You got vias in a lot of places. Just keep drawing, okay? Those are vias. It's just P plus and metal 1. And vias. Any questions on this? Cool. Now look at the new ones I just gave to you. There are 2 with solutions. Let's see if that makes sense. Oh, 4 examples. 4 more examples. A bit more practice, which is good. What is this?
That's a diode.
Yeah, it looks like a diode. Even though we don't usually design the diode in that way, but it is a diode. So see that when you are drawing this cross-sectional view, make sure this is accurate. Okay, so the active layer is right here. Align to the active layer, not the select layer, not the unselect or p-select. Okay. This one, ignore the via here. Is ghost via is nothing. What's that?
In that case, like, so you're the above one, when you're talking about like lining up the in select and the p select, so that you kind of overlap. If you're trying to make something like that, would you do like would you do the in select layer first and then like overlap with the p select, or are you trying to really line those up in the center there?
Good question. So you are talking about doping N plus or P plus in a different time, or
Like
doing
right
this-
next to each other. Like right
Yeah.
in this case, you're doing them right next to each other, where there's no boundary for error. There's no more overlap with your like p act.
Let me think of the process, see if I can figure that out.
Or is that splitting hairs?
Usually, I have never seen something have a direct contact between each other. So this is probably just something from the textbook.
Just a textbook. Okay.
Yeah, I mean, how could we make them exactly next to each other, right? No, I don't think that's possible.
You wouldn't do something.
I'll see if Dr. Jason can know something about that, but I
You
don't
just
think
probably
so.
wouldn't do something like that.
Yeah, I'll show you how the transistors are made, how the diodes are made. So it's usually, if you look at the wafer like this from the top, right? You do a P plus first, and you dope N plus in the middle.
Okay.
I have a contact here and contact here, and a wire going up. Now this is from top. You can imagine it's going up. You know what I mean? So you have P well, dope a P well first, and then dope an area N plus in the middle of the P plus. But still, I mean, which one should go first?
I guess it depends
That's a
on.
good question.
I guess it depends on what you need more concentration later on, because you're gonna have to overdope, because it's probably gonna leak into one side. You're gonna have to account for that gradient.
Yeah. Or I'm thinking, what I'm thinking is if you dope an N plus material in the P plus area, plus is gonna start neutralize it first, and then it goes to the other direction. You know what I mean? Is that possible? So I think that's what happens, because you can see here, it's a P-type wafer. We can still dope it heavily with N plus concentration here to make it N plus, right? And same thing here for the N wells. I'm pretty sure that's what happens. So you can see the N well is N plus materials, N plus in the silicon, and we can make either P plus or N plus in it without any problems. Okay, I think that's doable. That's how that works, I think.
Yeah.
Yeah. Yeah. To answer Luke's question, I think it's gonna be, so the way diodes are going to be like this, not this. I don't think it's gonna happen. Just right next to each other. It's too difficult. All right. This one. It's the easier one. There's no diffusion, no P select, unselect, P act, unact. It's just a poly and metal, so Fox is not being opened up. Duck drew a poly and metal one, and the via in the middle. Okay, easy. Next. it's unselect, it's unplus material within the unwell, and the unwell has a certain area here, like this. It's a weird shape. And it's drawing a cross-section here, which is just unplus only, not even unwell. So it's unselect unact, and that's why you have an opening here, aligned with the unact and the fox, but nothing else. So I'm gonna ask you guys to draw this and turn it in. Okay, let's do this right now.
Do you want us to just draw that over the old?
Just next to it. Oh, yeah.
Like over the other.
I think that works. Yeah, I think
Since
that
it
works.
just kind of adds on.
Let's do it. Yeah. But the fox will be, fox will be the same.
Mhm.
Yeah, doable. Let's do that. For this one, the solution is given. See if you can draw up one here, just slightly above that wear, and turn it in. No matter one, okay? No matter one, just above the unselect and p-select, unselect and unact. And there's unwell. Okay. Now I'm gonna figure out a problem for you guys to finish for the quiz. A real world problem instead of something printed on the paper. Okay. So this is it's called the transmission line. It has a PMOS on top and NMOS at the bottom. You can see that. Let me zoom in. Okay. So the pink one is the poly, and the light blue color is metal one. It's a poly. And it's a poly and metal one contact. So it's basically having a via, which is a little square here, and the bigger square is the actual metal one. But the thing is, if you place this, you can tell from this color, right? You place that light blue on the top of the pink, you're showing this color. So you can tell this is actually a metal one. The bigger square is metal one. So this little connector for poly, it's actually called a poly to metal one via. So whenever you are trying to connect the ports to the gate, because the gate requires some signal to turn it on, like voltage source, right? So you eventually need the metal to connect to it. So in that case, when you have all the gates or the poly here, and you do need a metal one with it. So this is actually a component from the library. I grab it, resize it, and connect poly from here to here, because this one has both poly and metal one and the via. So if I want to connect a port to it, or start, shorting into some of the signals with the metals, then I can directly left click and right click to introduce the metal one from it, because it has metal one over here already. So if I draw a line here,
What do you want us to draw this?
draw on the paper, just find a space on the back or something.
Fine.
And then what's the green and yellow?
Yeah. So green is P act. Yellow is probably the dash line is probably P select. And the dots, let me show you here. So these dots, right? See the dots? That's unwell. Okay, so the big area here is unwell. So all these are unwells. See these dots? Unwells. And that's the via. And you can see this color is a little bit darker green. Here, this darker green, right, for this box. It's just because you have the light blue on the top of the green color is showing this color, but that's just basically metal one wire on the top of the vias. Does that make sense?
Yeah.
What was the green again?
Green is the P what? P act, yes.
What was the yellow or pink again?
What's the what?
Pink?
Pink. Pink is the poly. Because you see the poly is being placed over here, and when you do a P act doping, it's gonna block it, even though the entire green box covers everything, but underneath the poly will be nothing. Because the poly will be placed there first.
And then what was the yellow again?
Yellow, there's no yellow. Sorry. Where's yellow?
It's like
Oh,
the
this one.
Yeah.
This is a P select.
P select. Okay. It's P.
Okay, P select is a bigger box. P act, right, is a active P plus area. Metal one, the light blue metal one. Vias. That via, keep in mind, it's P plus to metal one via. It's directly going up. Poly goes through. That's why it shows this weird color, because it's an overlay on the top of the green. Here, this one, make sure you do it correctly, because it has 3 different layers: poly, metal one, and via.
And then anything that doesn't have anything else, any of the inwell on it is Fox, right?
Yes. since I didn't print this out, since I don't have a color printer, and so if the sizes are a bit different, it'll be fine. I'll grade this leniently. As long as it shows the concept, the layers, dimensions are not dimensions, the layers are correct, you'll be fine. You can ask questions. You can refer to the notes, refer to the in-class exercise. It's fine. What's that?
Does the metal one cover the fuselage? Like.
Yeah, it's on the top.
Okay. Like, well, I meant like in the manufacturing process. Let's say you're doping the P-select. You put the metal on afterwards. The P-select would be under the metal, like fully, unlike where.
Yeah, it's the bottom up. So whenever the P select and P plus are done, you put the insulation layer and with the poly, and you will never be able to do anything else with the bottom anymore. It's done. It's covered.
Yeah.
So start doing metal 1, metal 2.
Okay. I was thinking about like how to draw it. 'Cause I think there's.
Auto joy.
I think there'd be gaps in the P select, right? Due to the poly.
P select is not really opening up the opening up the fox, right? So
Yeah.
actually outside of the P select, the dashed yellow line will be O fox
Yeah.
at that layer. And I mean, we are drawing anything above the P plus, you don't really care about the bottom, the lower layer anymore. You just start drawing the correct width of the metal.
Yeah.
Right? You don't care about the bottom anymore. The bottom is done. It's already sealed or covered.